Good afternoon, or almost good afternoon, pre-calculus students. Can everybody hear the audio well, or can you hear me?
Yes.
Yes, I can hear you.
Thank you. Now, what we have to do today is actually interesting in that we get to use a lot of the ideas that we've been working on in the past few lectures. We find that the theory of equations when it comes to polynomials is very rich in lots of nice techniques, but it still can be very confounding when we're trying to find zeros of certain polynomials. So that's always a challenging task. So what I want to do first is to take a little excursion to 3.7. Remember, I said I was going to talk about 3.7 at least in passing. Basically, it covers inequalities that we did in the first chapter, but there are some cases where you can use the techniques that we have learned in chapter 3 to make the process of computing the BVs a little bit easier. So I want to start with that, and then we're going to go and do a little review and work on rational expressions and understand how we can use the theory that we've already developed in this chapter, and then possibly add a few new ideas that maybe you didn't pick up in your college algebra course. So let's go ahead and look at that inequality. I'll share my screen. So lots of times when it comes to doing mathematics, you think, well, you know, I've done this before, or I've seen this before, I don't need to study it. But what I think is nice about some of these problems in this particular section is that you really don't have to learn any new mathematics. You just have to think about applying what you have learned.
I can't hear you.
Oh, you can't hear me? Oh, let me check this. Let's see here.
I can hear you.
Yeah, I can hear you too.
Can you hear me? Oh, okay, okay. All right, that's good. I just want to make sure. All right. Can everybody hear me now?
You're
Yes.
good.
Okay, good. Well, you know, it must be the after effects of all the rain. Yeah, the rain is not good on electronics. Where I'm organist at First Presbyterian, the AC always goes out. So I've just stopped telling them that it doesn't work and just do with it as it is. So now what I want to do is look at this particular example. We have x cubed plus x squared minus 50x plus 48 is greater than or equal to 0. Now, when you look at this particular problem, and of course, when we solve the inequality, we're going to solve this in R. We know about imaginary zeros and we know about complete factorization, and that's a very useful technique. But in this particular case, what we see is we have a setup that's really tailor-made for our BV technique. That is, we already have the 0 here, and then we have this polynomial. Now, what's different when we compare this to problems we've done in the past is that we didn't have a cubic polynomial like this that might require other techniques. So when you look at this, it's like, well, I don't think we could really factor it by grouping. So we want to use the rational zeros theorem to see if we can uncover the BVs. So first, notice the constant term is 48. So the P would have to divide the 48. And the leading coefficient is 1. So the Q, which is the denominator of the possible rational zero, would have to divide 1. So now this just implies that we're looking at multiples of 48. So we could say 48, this is 6 times 8, And so that would be a 2 times a 3. And then, of course, we get 2, 2, and 2, 3 copies there. So that would be 2 to the 4th times 3. That's how we would start constructing the possible rational zeros. So we've got a pretty big list, plus and minus. But we're thinking, you know, this is a nice looking polynomial. We're not going to write down every possible list. So what I thought I would do, and this turned out to be one of those problems where you just get something that falls out of the sky. Notice we can go ahead and write our coefficients in descending order. Now, you know, with your WebAssign, you get the practice of writing down all the possible candidates, the pluses and minuses and things. And so we would start, our list would start this way. For instance, we could have a plus or minus 1, and then we'd have a plus or minus 2, and then a plus or minus 3, and then a plus or minus 4, etc. Okay? And lots of factors there. But like I said before, sometimes when you start, I always encourage you to begin with the smaller numbers and make some observations. And now what we can see when we look at this polynomial, because I always say don't try numbers you know that don't work. But look here, we have a negative 50, and then we have a 48, a 1, and a 1. So we have a 50 plus a negative 50 when we sum the coefficients. That's equal to 0. So when you look at this, you're like, okay, 1 is a 0. So like I said before, you don't try 1 when you know it doesn't work, because you can easily scan the coefficients and figure out when it does work, or whatever the case may be. But so that's a freebie. So now we can just go ahead and check 1 because we know it's 0 and get the reduced quadratic. So I'll just say check 1, and let me answer the door, kids. I've got to let the bug man in. Just 1 minute. Coming. Oh, I'm good. I'm just doing a virtual lecture. See you later. You too. All right, so I'm back. With the rain, you get more bugs, so you need to have the pest control come. So now we bring the 1 down. So we have 1 times 1. That gives us a 1 plus 1. That gives us a 2. And then we have 2 times 1, which is a 2, plus a negative 50 is a negative 48. And now when you multiply, of course, we know this is going to work. This will be a negative 48 plus 48, which is 0. So now there's our reduced. So this implies, or equivalently, we have x minus 1 times x squared plus 2x minus 48. So I think the key with the WebAssign with these particular problems is that the author is making an effort to infuse some of the newer techniques into this process. So now whatever you know, you can use. And of course, this is an easy AC. If we see AC is 1 times the negative 48, we can use the positive 8 and the negative 6, just ignore the 1. And that will give us the sum here. So this makes for an easy factorization. So we have x plus 8 and x minus 6. So another thing that we realize with the rational zeros theorem is that it basically clues us into techniques that actually make sense for us. And here's the thing that's interesting here. We have another positive 0 here. And notice the rational zeros theorem, bounds theorem, or actually the bounds theorem has a negative here. This is not alternating. And these are not, well, we're not alternating. We don't worry about that. We don't get a list of non-negative. So this is basically saying that right now, this is not considered an upper bound for the real zeros. So this would give us a reason to keep checking. For instance, just comparing to what we've already done. But since we hit the jackpot with the 1, we're done. And now we have the BBs. So this gives us a 1, a 6, and a -8. So what's nice is now that all this is coming together, we can use all the different techniques. Now, of course, we do our number line. So we have a -8. And of course, these are all nice zeros. We can use our multiplicity understanding. So again, don't worry about the equal spacing, just numeric order. Now, one thing we can notice is we can use our end behavior with the polynomials. This has a leading coefficient of 1, so we know that the end behavior, let's just say the limit as x approaches -infinity, and if you like, we can just call this p of x, will give us -infinity because we're raising a number that's small, very negative, to an odd power to give us a -infinity. And then we're done. We don't even need to do anymore. And let me show you why. Notice all of these zeros here have multiplicity 1. And this is even going to work for rational expressions. So here we're below the x-axis, we're negative. And then we have to cross like we've done before. And then we have to cross again. And then we have to cross again because these are all odd multiplicity. Now, even with the rational expressions, we're still going to try to do this, but we'll just have to be careful that we don't cross vertical asymptotes. And I'll talk more about that. But now we see we have negative, we have plus, we have minus, and we have plus. Now, of course, you could still look at this like I do in the Smart Pen videos. We'd have a -10 here. Say we could have a -3 here, and maybe a 4 here and a 10 here. So you can still check, you'll get the same thing. It's just now we're using some different ideas. But I would say this, don't ever try a technique when you don't feel really confident about it. So for instance, if we were wanting to get this plus here, we could try the -3. So we would have a negative in the first one, and then a positive, and then here a negative. And then the two negatives give the positive, so we would get that. So the idea here, sometimes maybe what we want to do is use some other ideas that we've developed in this course to analyze a little bit differently. And you're certainly welcome to do that. I always tell my students, if this makes sense, fine. But if you would rather check the factors, you have that at your disposal. Just don't look at this as, well, I have to do this exactly like Professor Ron says. No, I'm just giving you techniques that you can use to supplement what you already know. Now, when we go back to the top here, we see that we either need plus or equal to 0. So these all get pluses, or excuse me, all checks, because they give us equal to 0. And then, of course, the plus here is good, and the plus here is good. So now this will imply that WebAssign will say, okay, write your solution set in interval notation. Again, you're already getting better at typing and writing your responses correctly. Just remember, the correct response is the right response. And when you're writing, you know, just think about, you know, when you're writing a test in class and you get sloppy and you don't write what you mean and it's wrong, and then you get upset, and it's like, well, you've got to do quality work. So we have to make sure that what we're putting here is good work. Now, so now we look at this and say we've got a check at the -8. And we need the bracket because we want to include it. And then we want to extend to 1. So in this case, we have a 1 with the bracket. And then we want to combine this with the next set, which starts at 6 with the bracket inclusive to infinity with parentheses. So again, devoid of the rational zeros theorem, this is something you already know how to do. But you don't get bored with this because, again, this is just a basic technique in pre-calculus. And it is a basic technique that you will continue to use in Calculus 1, mostly in Calculus 1 and Calculus 3. You do use this some in Cal 2, but Cal 2 is pretty much a topics course. And you really see this more in Cal 1 and Cal 3. So we're going to come back to this, something like this at the end of the class, just to do a recap of some other ideas that we want to review with this. So I want you to look at this section as basically review and refinement of what you already know how to do with the BB technique that we have here. And again, like I say, use what you know. Now, what we want to do is talk about a situation having to do with the rational function. Now, rational functions are ratios, and what I did, I put a little composite list here of some things that I want you to know about rational functions. And of course, a really good way summary of all of this outside of looking at the Smart Pen videos is the set of PowerPoints. PowerPoints give you some nice little summaries of all of the items that we talk about in this class. And so feel free to use those. They often make great for lectures, you know, to showcase some things. But I went ahead and just wrote this out. You can find all of this in the PowerPoints. But I wanted to basically give you the new ideas that we're going to need for the rational functions. And again, this is review from college algebra, but I'm sure it's gotten a little bit rusty. So what I did here is I want to reinforce the fact a lot of times when I do rational functions, I'll use an uppercase R or a lowercase r, just basically R for rational. So what I did, I checked in your WebAssign and saw that they were just using the lowercase r, so I'll use that here. And so when we think of a rational function, we think of a function that is a ratio of two polynomials. And what I've done here is I've used the P and the Q that we were using in the rational zeros theorem. So rational function, ratio of two polynomials. So we got the sign testing technique. We have X and Y intercepts. That doesn't change. What is the new object here that we need to consider with these functions? And they're asymptotes. So what I've done here is I've summarized both. Again, when we get to calculus, we'll be able to get more information here, but for now, this will be more than enough. So we're going to let R be a rational function like we've defined here. And we're going to say the vertical line X equals C. Now, I can't say this enough. It's like saying the vertex is, you know, H comma K. It's a point. A vertical line is the equation of a line. So we're going to say that the vertical line X equals C is a vertical asymptote of the rational function if and only if. And here are the conditions. Q of C, that is the denominator, is actually 0. C is a 0 of Q, but it is not a 0 of P. That basically defines the existence of the vertical asymptote, considering the fact that we have other elements in the domain around C. That is, what we're assuming here with these problems is that we have a very rich domain. That is, we can approach C from either side. Maybe it's just one side, but normally we will be able to allow X to approach C from the left side. I use the negative as approach from the left, and the right side approach here with the positive from the right. Now, why do we care? Why is this even important? Well, this is what we're going to actually prove in calculus, but for now, we'll assume that our intuition supports this. the values of R become infinite as X approaches C. And you're thinking, oh, this is like the end behavior, where we look at the dominant term and try to figure out what sign we attach to infinity. Well, we already know how to do this. That is, we're going to have one or both of these cases occurring. And when X approaches C from the right or the left, we're going to get either plus or minus infinity. That is, the value of the function gets arbitrarily large or infinitesimally small. And we will determine the sign of infinity using the sign test, just like we do with the BBs. So we will use the sign test, like we're solving an inequality. So that makes this process very simple. Students like the vertical asymptotes because it's just like finding the domain. When you compute the domain of a rational function, you basically want to exclude the real numbers that make the denominator 0. And then you have the domain. So when you compute the domain, you may actually be defining some vertical asymptotes. But the main condition is this, and I can't say this enough. The denominator is 0, but the numerator is not 0. And with calculus, in this particular neighborhood of C, we can actually prove using basic arithmetic of the limit that the function actually becomes unbounded. Basically, ladies and gentlemen, when you show that something is unbounded, you just pick some positive number, call it M, and you show that you can make the function bigger than that positive number. And since the positive number is arbitrary, that will prove that the function becomes infinite. It's kind of like, wouldn't it be nice to know that that the money from your job was infinite? Like you could say, okay, well, I need this much money this month, and so I'll just let it be what I need it to be. Unfortunately, that's not the case. That's when we would like the calculus to work in our behest, so to speak. But yeah, whatever, my poor attempt at humor, but still, sometimes the math helps us, sometimes it doesn't. Okay, so the vertical asymptotes are relatively straightforward, and we'll do some examples with that. Now, and notice what I've written here, ladies and gentlemen, infinite limits. We've talked about this before. The limits are infinite. So they're not technically real limits, but they are quasi-limits in the sense that they tell us that the function is becoming unbounded either positively or negatively. Now, the other step that we need to consider will be the horizontal asymptotes. Now, this is another thing that you did in college algebra, and it does require calculus techniques, but we're going to focus on the very intuitive ideas here and then wait to calculus to actually prove some of this. So again, we're going to start with a rational function, and we're going to say the horizontal line y equals c is a horizontal asymptote of r of x if and only if. So we could have one or both. We have to have at least one. What that means is that as x becomes infinite, like we're doing in behavior, or x becomes infinitesimally small, the function values approach the c here, the c here. So you're thinking, okay, that's kind of different from the in behavior, because here we're getting limits at infinity that are actually finite numbers. I mean, like a 3 maybe, or a 1/2 or something. So you're thinking, okay, here with the vertical asymptotes, we get infinite limits. And here with the horizontal asymptotes, we actually get a limit at infinity that is truly a limit. That is a finite real number. So again, when we consider the horizontal asymptote, it's a little bit more complicated because once we get to this point, we're not like, okay, you know, it's not a zero of the numerator, we're done. Well, we got to do a little bit more work, but not a lot. Now, here are the rules that you learned in college algebra. And again, these are based upon the dominant term. So if we have P over Q, how do we know when we have a horizontal asymptote? Well, in the first case, if the degree of the numerator is less than the degree of the denominator, 1 is less than 2, 0 is less than 1, something like that, then we automatically get the x-axis or y equals 0 as a horizontal asymptote. That's automatic. No work past that. So when you're checking your rational function, if the degree upstairs is less than the degree downstairs, numerator, denominator, then this is automatic. And that just has to do with the fact that the dominant term in the denominator has a larger power of x, and therefore it does dominate, and it forces the value of the function to converge to 0. Okay, that's something we can prove with calculus. Now, the next condition for a horizontal asymptote is number 2 here. That is when the degree of the numerator equals the degree of the denominator. That's another case of a horizontal asymptote. How do we get it? Like I've said before, and I've alluded to this in the first and second week. We take the ratio of the leading coefficients. So what I've done here, I've used A's for the P coefficients, and I've used B's for the Q coefficients. So when we take the ratio of the leading coefficients, and in this case, this would mean that M and M would be equal, we get the horizontal asymptote, and we set that equal to the Y. So again, we get a horizontal line that's different from the x-axis. Okay, so again, I said this is more work, but it's really not a lot of work. It just gives us a way. For instance, we think about the fact that the graph will approach the asymptote when it's vertical. The graph will approach the horizontal asymptote. Okay, that helps us draw the graph. Again, like plotting intercepts. And then for the third case here, which is not a horizontal asymptote, but it's a case that we're going to discuss, this is when the degree of the numerator is 1 more than the degree of the denominator. And some of you were already asking me about this. In this case, there is no horizontal asymptote. We get what we call a slant asymptote. That is, we get a line, but it's not horizontal. It has a non-zero slope, so it's slanted. That's why we call it a slant asymptote. Sometimes it's even called oblique asymptote. And how do we get it? We divide. We just take the quotient. That is, when you divide the polynomials with degrees like this, the quotient will be a first degree polynomial. And so you disregard the remainder and you just take the q of x from the division algorithm. So if you can use synthetic, fine, that makes it even easier to get the quotient, and you just set that equal to y. So the nice part about the horizontal asymptotes is that they utilize what you already know about polynomials and take it to the next level. So both of these topics are really calculus topics, but as pre-calculus students, we can intuit all of these and actually draw some graphs that are reasonable, but lack some refinement, okay? We can get a fairly good graph, but just like the polynomials, we have to accept that there are certain attributes that we don't know at this point that will require the calculus, but we're okay. We'll be able to make it. We have to start somewhere. So now let's look at some examples here. Now, the very first one, it's funny. lots of times when you start out with these, the simple ones are what confound everybody. So I want us to do this particular WebAssign problem like we're attacking it with what I just taught you, not with transformations. So let's say we have R of X equals 1 divided by X plus 4. Now, when we look at this, move this over so I've got the mouse on the left side of my screen. When we look at this, we say, okay, this is a very simple rational function. We can think in this case that we have P of X divided by Q of X. And so P of X is 1 and Q of X is X plus 4. Okay, well, that's a rational function. And so we say degree of P. Well, the degree of the constant polynomial, that's just 0 by definition. And then, of course, the degree of Q is just 1. Now, 0 is less than 1. I mean, that's pretty profound when you think about it. We have to understand the number system, but I'm just making a point. The degree of P is less than the degree of Q. So this implies that we have case 1. We have y equals 0 is the HA, the horizontal asymptote. So usually what I say, I'll just list these and we'll go through them. But it's important to analyze what you have and just say, even in this simple case, we know we have a horizontal asymptote and it is the x-axis. That is, the line equation is y equals 0. Be very careful. Do not say that the horizontal asymptote is the number 0. That is wrong. That is incorrect. It is a line, y equal, okay? It's not the most concerning thing when you send me messages and you have done things like this. Be very careful. Think about what you're typing. Think about what you're writing on your paper, because the correct mathematics is important. And I know you know this. It's just so easy to get careless. Now we think, all right, well, let's look at the denominator here. We see that Q of -4 equals 0. That is, -4 is a 0, but P of -4 does not equal 0. So I'm kind of fleshing this out a little bit more to make the point. By definition, we have a vertical asymptote, and so we say VA X equals -4. Okay? Now, very simple, but very important. We will do this regardless of how much stuff we have. If there's more stuff, that means we have a little bit more to think about, but we analyze it the same. Now we're thinking, okay, well, what else do we need? What do we get when we do our cheat graph? Well, we need a sign test, but before we do that, let's go ahead and find some intercepts if there are any. Now, when we look at the x-intercepts, we're thinking, when does the P of X equal 0? Well, that's always 1, so we know we don't have any there. The graph cannot cross the x-axis because 1 is never equal to 0. And then the y-intercept, well, that's even easier. That's just R of 0. And we're thinking, well, we haven't even computed the domain. We're assuming that 0 is in it. It is. When you replace X with 0, you just get 1/4. So now, when you look at this, at least intuitively, we have a domain of R is going to be all reals except what? -4. All reals except -4. And then, at least intuitively, it looks like we're going to hit any real number because of this vertical asymptote except 0, because the numerator can never be 0. So the range of R would be all real numbers except 0. Now, sometimes we have to make some adjustments, and we're going to see that today. Not all rational functions exhibit the same type of characteristics, even though we'd like to think they would. We have to be careful. So now you're thinking, well, we're good to go. We've got the asymptotes, we've got the intercepts. The only thing we need is just a little sign test. Now there's not much here. The only BV is -4. But like we're thinking, okay, -10, +10. But when we look here, we're thinking that just occurs to the first power. So the sign will change, but it's not going to change by crossing. It'll just change because this has an odd power. So then we're thinking if we've got -10 here, we're below the x-axis. So we're thinking negative, but we don't cross, so we do something like this. So I don't draw through there, basically to say that we never cross a vertical asymptote, but we know that the sign has to change, because we can think of this either as just checking the sign of each of the factors, or we can think of this as like a multiplicity 1, because it is a 0 in the denominator. So we're forced to see that sign change. So this will give us, though minimal, enough information to get a reasonable graph. Now, when we draw the graph, you're thinking, how do we draw it? Well, these graphs are actually differentiable where they are defined. What does that mean, ladies and gentlemen? A differentiable graph is smooth, okay? It's not jagged, okay? So that's why we cheat and draw them smooth. So let's go ahead and draw our axes. Sometimes the simplest example can show you all kinds of ideas. So now when we look at this, we have a vertical asymptote at -4. So we don't have to worry so much about the scale here. This is an easy scale. So we'll do -4. So we have x equals -4. And now, when we go up to our intercepts, we'll spread this out a little bit. So we'll have like a 1 and a 2. So here's -4, and we'll call this 1 and 2 just to spread it out a little bit. So now, when we look for our y-intercept, we're right here about 1/4. So I'll do that in red. So now, when we look at this, we know that we have to approach the vertical line x equal -4 in an infinite case, that is in the positive infinite, hugging this way, then pick up this point and then hug the y-axis, excuse me, the x-axis. So let me just go ahead and write this as y equals 0. So now we've actually specified the horizontal asymptote. So now we can draw what's going to happen here. Approach, and then get really close to the x-axis like this. So now we drew it nice and smooth because Professor Ron told us to do that, but that's because the calculus tells us that it's smooth. We can't prove that in this course. And so we approach the line x equal -4 in the positive infinite case because of the sign test. And then for the left approach, so you can think right, left, we have to go to the negative infinity direction. But then above, we have to approach y equals 0. But again, there are no x intercepts here. So we just hug and then hug this line. So we can easily do that. So the part that's called cheating is, like I said, the smooth part. And then you look at this and say, well, isn't this like one of the functions we proved before that was 1-to-1? So again, when we draw a graph, we're just trying to give a reasonable picture. The graph is not a proof of anything. It does not prove anything. Everyone always says, well, if I can draw the graph, here I go again, but I'm saying this for a reason. If I could draw the graph, I would know whether or not it was one-to-one. No, you wouldn't, because you know it's one-to-one by proving that. The graph does not prove a thing. You have to know that it's one-to-one when you draw it, but we're not really focused so much on that. We draw this using the basic concepts that we have. That is, the graph must approach the vertical asymptote as x gets near to -4 from the right and the left. So our picture must look like this. The graph must approach y equals 0 as x becomes arbitrarily large and arbitrarily small. So the graph must look like this. And then we figure out, is it above or below with the sign test? So at least from a standpoint of a reasonable graph, this is not half bad. But we really don't know what the shape is here. We drew it this way, but why does it have that shape here? And why does it have that shape here? And why does it appear to always be decreasing? We think it's decreasing, but how would we ever know that? That will depend on the calculus, okay? So just by knowing that the graphs approach or become arbitrarily close to asymptotes helps us to draw this. So we're utilizing a lot of intuition, but we're taking advantage of all of this because when we get to calculus, none of this will be forgotten. We will more easily refine this graph when we get to calculus. And there might be a question on the test that goes just like this. We'll say, prove that this function decreases throughout its domain. And you won't be doing any of this. You will just simply be doing some calculus and then analyze the derivative based on how we've done here. So there are lots of questions in this problem. They could say, give the vertical asymptote, provide any horizontal asymptotes. What are the y-intercepts? What are the x-intercepts? So you can get a lot of questions out of this that you'll see in your WebAssign. But when you have time, go back and fill out all the details of the sketch on questions when you're not asked to actually sketch the graph, okay? Just to get some extra practice. Now, the next example looks like this. We want to look at the case where we actually get what we call the slant asymptote, and we want to see how we could actually do it. So this one is from your WebAssign. So we have t of x, here's an example. T of x equals x squared minus 2x minus 24, and the denominator is x minus 10. So what we want here are the same thing, asymptotes, intercepts, and a sketch. Again, computer-generated sketches are really beautiful because they plot so many points and they appear to provide a continuous graph. So again, when we draw our graphs, they don't have breaks in them unless we're encountering vertical asymptotes, and they're nice and smooth. So we're using continuity and differentiability from calculus. So there's so many things that will be answered when you take your next class. Now, notice here, we've got a P and a Q, but let's just do a little analysis here. The AC would just be 1 times a negative 24, but we're seeing we can just ignore the 1 and use a -6 and a 4. That will give us the -24, but the sum will give us the -2. So that's an easy factorization. So we have x minus 6 times x plus 4, just to go ahead and factor it. And then downstairs, we have x minus 10. So we're thinking of this as P of x over Q of x. You don't have to write that, but again, just do the analysis part. And then we say the degree of P is clearly 2. The degree of Q is clearly 1. So we say 2 equals 1 plus 1. That is, the degree of P is 1 more than the degree of Q. So this implies slant asymptote. Now this may be very simple, but if you don't look at it this way, you will ignore it. And you can certainly have quadratic asymptotes, you can have cubic asymptotes, you can have quartic asymptotes. We're not really going to spend much time with that. When you get to calculus, you'll see some of that at play. So the idea for right now, we're just going to focus on the slant asymptotes. Now, we can notice a couple of things here. Since the Q is actually an x minus c, we can find the quotient using the synthetic process. So that's a freebie. So let's go ahead and find the quotient that way. Otherwise, we'd have to just use the long division. So we have what? 1, -2, -24. And then, of course, the c is 10. So now bring the 1 down. 1 times 10 is 10. 10 plus -2 is 8. And then 10 times 8 is 80. And then if we subtract 20, we get 60, and another 4 gives us 56. Well, we don't care about the remainder. We just want the quotient. There's the quotient right there. Quotient. So this implies y equals x plus 8. There's the slant asymptote. It's the quotient. The quotient is the slant asymptote. That is, once we make it into that, it's like students will say, how do I compute this? Well, you figure out what the quotient is, and then you set that equal to y. So y equal the quotient, okay? So remember, the asymptotes are lines, and they must be written as lines. So don't put the slant asymptote is x plus 8. That is not correct. The slant asymptote is y equal x plus 8. I'm telling you this because you're going to make this mistake, and it's okay. But eventually you will have to come to grips with the fact that this is an actual line, okay? Now, let's see what else we have here. We've got our slant asymptote, not vertical, case 3. Now, what about vertical? Well, I went ahead and factored this so we wouldn't have to be so formal with this. We see that 10 is a 0 of the denominator, Q, but 10 is not a 0 in the numerator. So this would imply, that is, we see Q of 10 equals 0, but P of 10 does not equal 0. So this implies x equal 10 is a vertical asymptote right there. So by definition, we have a vertical asymptote. We have a slant asymptote as opposed to a horizontal asymptote. And now we just need the intercepts and a little sign test. So x-intercepts. Well, first off, we can see here that the numerator will be 0 when these factors are individually 0 by the 0 product. So of course we're going to get a 6 and we're going to get a -4. So these would be points on the x-axis where the actual graph crosses the x-axis. So when we think about, again, think about your WebAssign. Formally, the x-intercepts are 6 and -4, but WebAssign always has you write the ordered pair. to make you aware of the point associated with the intercepts. You know, when you have slope-intercept form, the b is the y-intercept. Again, it's a number, but WebAssign is having you associate with the intercepts the actual point. Now, y-intercept will just be t of 0. Again, we're assuming 0's in the domain, and it is. So now the easiest way is not to use this one, that 0, 0, 0. So we're just left with the negative 24 over negative 10. And of course, these are all divisible by 2. The negatives absorb, and that'll give us 12 over 5. And those are relatively prime. So this gives us what, 2 2/5. So just kind of a ballpark figure of where that would be on our graph. And now we would like to kind of see how all of this fits together with a sign test. So you can plot the vertical asymptotes, the slant asymptotes, and the intercepts, and maybe guess where the graph is. And in some cases, you wouldn't have to work very hard. But the sign test pretty much puts all that to rest. There's no guessing. And we can do a relatively efficient one. Notice all of these factors are first degree. So we would get a sign change at each of these zeros or undefined areas. So now let's see what we have. We've got a negative 4. And then we have a 6. And then we have the 10, which is kind of the no man's land. We think of the vertical asymptote as the black hole, so to speak, the infinite gravity. We don't cross the black hole. If we do, we're no more. We're no longer available. So now what we can do, we can think of like a negative 10, a 0, an 8, and maybe a positive 20. So since we're going to change at all of these with these multiplicities, we can just go ahead and check the negative 10 here. So we have the negative 10, we get negative 10 here, we get negative, and then of course negative 10 here, that's even more negative. So 3 negatives is negative. So this is below. So when we get to that negative 4, we've got a cross. And then when we get to the 6, again, we have to cross. And then, of course, when we get to the 10, we don't cross, but we change sign. So we have negative, positive, negative, positive. So now what we're seeing as we approach the vertical asymptote on either side, on the left, we're at negative infinity, and on the right, we're at positive infinity. So this really covers all the bases. Now, the only thing we need to do now, just like the last problem, is just sketch in the asymptotes and the intercepts, and we'll be done. So let's spread it out a little bit. A nice long x-axis, and then a y-axis. Now we've got the, what is it? Y equal x plus 8. So, and then we go out to 10. So let's give more space down here. So there's our y-axis. And if you like, since we don't have infinite amounts of space on our paper, we've got the 10 here. So let's just go out in 5s. So we have like a 5. And let's see, we're going to have a 6. So we'll put the 6 there, and then we'll have like a, go out in 5, so a 10 there, and then like 15. And so then we've got a 6 and a negative 4. So we'll be like, say, a negative 5 here. And then we need the x-intercept here, or the y-intercept, which is 8. So let's do like about any other small numbers. No, they're not very small. We got 2.5. So we'll do like 5. And a 10. So spread it out a little bit. And so that'll give us the 8, say like 6, 7, 8, 9. So 8 about right there to help us with our y-intercept for our slant asymptote. And then let's see the -4 for the x-intercept about right there. And then we're going to have the 6 about right there. So let's go ahead and sketch. Oh, and then of course, as we run this back to -8, so let's see, negative, yeah, my scale's kind of wonky here. I'm sorry, I'm not keeping it as equivalent to this side. So we'll do like about -8 about right here. So we can go ahead and sketch the slant asymptote. So I'm not going to have much room for my graph up here. It's going to be up in the atmosphere. So here's my x equal 10. And now for the y-intercept, we have 2 fifths. So we'll say 1, 2, about right here. And let me go ahead and extend this here. Just kind of go through our sign test. Okay. So now we've got to hug the slant asymptote. We've got to pick up these points and then head back down here using the sign test, -infinity on the left side of 10. So we can now use the definition of the asymptote. Like that. Now, we don't really know what the maximum point is here. It could be here, it could be around here. That's where the calculus is going to be necessary. So we can sketch here a nice smooth curve to pick up these points. And then over here, we've got above the x-axis, so the graph's going to be up here. There's not much room for it, about right up here. You keep going on forever. So again, when we think about this, we have to hug this and we've got to hug this. We can't do down here because again, we've got positive infinity. So we have to hug here and then hug there. And another thing, we don't cross this slant asymptote. We can prove that. We're going to have another example where we actually test this. But what's interesting about this example is that now we have a function, at least as we've drawn it, it doesn't look like it's one-to-one. We have to prove that because we're seeing that we get repetition of range values here and even here. And so the calculus would have to support the fact that our particular curve is nice and smooth. It appears that it's increasing here and then eventually decreasing. Here, it appears for some amount interval, it's decreasing and then increasing. So in order to find this relative minimum or a relative maximum, we would have to find the existence of horizontal tangents. And like I said before, we don't know that with what we're doing here. So now what we see is we have a nice graph with the slant asymptote that we've been able to do just by doing the basic computations here. So in summary, we get the slant asymptote because of the relationships of the degrees. The degree of P, the numerator, is one more than the degree of the denominator Q. So we can divide using synthetic because we have a simple x minus c polynomial. The quotient gives us how we construct the actual slant asymptote here. And that would be something you could label. You could just say y equals x plus 8 like we've labeled this. So we've got our slant asymptote, then we get our vertical, and then we go ahead and get our X and Y intercepts, X, Y, and then the sign test. So this basically directs us, again, we really didn't need the sign test for this part, ladies and gentlemen, because we know the graph has to pick up these points. And so it's got to exist on this side. And so now we can see, I'll go ahead and plot this right here. That's a -4. And so we see at -4, the graph is above the x-axis all the way to 6, above, positive, and then it becomes negative again here and here. And then in this part, it's always positive, so it's up here. And again, it can't be down here because it's got to hug from the positive infinite sense, the vertical asymptote x equal 10 from the what? Right side. So this is going to be very handy in calculus. But the problem, they say, determine all relative extrema of this particular function. And basically what you would be determining is the value of the function here and the value of the function here. And that will require calculus, like I said before, where you actually determine the horizontal tangent lines. So again, with a computer, we can plot 1,000 points and get what appears to be a really nice graph. But again, the graph doesn't tell us anything. The plots don't tell us anything. You know, you can utilize the technology to approximate things because they have built-in codes like Newton's method, which is a calculus routine of second order to approximate zeros. So again, look how much output we can get from just the basics that we know. But then we look forward to what we can do when we get to Calculus 1 and fill in all the details. So this is a whole lot of output for very little input. And we're fine with that. Now, what I want to do is look at a situation that reminds us of what we did when we were talking about invertible functions. So we had an example like this, where we had r of x, and this would be like prove that this is 1-to-1. We have 2x plus 8 divided by -8x plus 4. Now, what's good about this is that we're comfortable with the fact that if we think of this as a p of x over a q of x, we have two polynomials of the same degree. That is, they both have degree 1. So before I do any analysis of this, I can just say degree of p equals 1 equals degree of q. These are all the same degree. And so we think, okay, well, what does this give us? So now we think, all right, so horizontal asymptote, ratio of leading coefficients. So we have 2 to -8. So we said y equals 2 to -8, which is -1/4. So ratio of leading coefficients. So the beauty of calculating the horizontal or slant is that it's kind of tailor-made to our rules list, which says, how do degrees of P and Q relate? So before we do any more with this, let's just go ahead and factor things. We've got the horizontal asymptote. Let's just factor the 2 upstairs. And then we can factor the -8 downstairs. And so we divide 4 by -8, that'll give us a -1/2. And then of course the 2 will divide into the -8. So we get x plus 4 divided by -4 times x minus 1/2. So just doing a little bit of arithmetic here, now kind of carries through to the fact that we can see what the x-intercepts are and we can see what the vertical asymptotes are. So I would say when we look at a problem like this, I think the first thing that this does, this reminds you of some of the functions we did with the invertibles, where when we had the degree 1 and basically the fraction, we ended up with a one-to-one function because we could easily prove that. Now we're thinking, okay, well, we have a 0 of q here, which is 1/2, which is not a 0 of p. So we have vertical asymptote x equals 1/2. Again, 1/2 is a 0 of the denominator, but 1/2 is not a 0 of the numerator. And then we have x-intercept. Again, we look at our factor form and we see, when is this fraction equal to 0? When x equals -4. -4. So when you factor things, it's easy to see. And then we have for our y-intercept, which would basically go back to the original function, we have r of 0. So now we can forget this, go back to this. These are both 0, so we get 8/4, which is 2. So we have an x-intercept, a y-intercept, we have a vertical asymptote, and we have a horizontal asymptote. And then, just like before, let's go ahead and do a sign test. What are the BVs? We've got what? 1/2 and -4. So -4, 1/2. So now we've got all these negatives running around. So let's just test this side, and then these are just first degree, right? So we know that the sign will have to flip. But let's go ahead and say we got a -10, say a -2, and maybe a 3. So notice if we put in the -10 here, that's a negative. And then of course we have a negative already built in, so we can't ignore that. And then a -10 there is negative. So 3 negatives is negative. So we're going to have to cross at -4. And then we're going to change sign here, but we won't cross. We'll do something like this. So we've got plus, negative. So now when we think about the vertical asymptote, we will be positively infinite to the left of 1/2, and will be negatively infinite to the right of 1/2. So as we approach like this, positive infinity, we approach from the right, negative infinity. So that kind of gives us a little roadmap as to what we need to do with the signs. And now again, this, if you go back in your notes, you can see that we would have proved that a function like this is actually 1-to-1. We can prove that. Now our graph will probably look 1-to-1, but it won't be because we were focused on that. It'll just be because we remembered proving functions like this having that 1-to-1 property and therefore being invertible. So let's go ahead and draw some axes. So now we've got a vertical asymptote at 1/2, and we've got x-intercept at -4. So let's spread this out just a little bit, and then we've got that, what is it, -1/4. So we'll say like, so like 1, 2, 3, 4, and then 1, 2, 3, to get the -4 right there. So we've got a -4. Well, let me not write that in right yet. Let me just, I'll do it later once we draw it. And then we've got the horizontal asymptote. So we'll spread this out a little bit. We'll say there's 1 there and -1 here to give us a little more space. So I'll cheat a little bit and put my horizontal asymptote about right there. Just spread it out a little bit. So we have y equals negative 1/4. And then we have the vertical asymptote x equal 1/2 right here. So like halfway in between. So let's go ahead and draw that. So this gives us x equals 1/2. And now we can fill in our intercepts. So we've got 1, 2, 3, 4, right there, negative 4. And then we have the y-intercept of 2. Now, what we're noticing here is to the left of negative 4, we're below the x-axis, but we have to hug the asymptote. So we hug the asymptote and then cross and pick up that point and go to positive infinity. That. So we get a curve that's approaching the asymptote y equal negative 1/4, crosses at negative 4, and then moves off to infinity, becomes infinite as x approaches 1/2 from the left. So now I can go ahead and kind of mark that negative 4, 2, so we easily see that. So the nice part about this is that when you do the calculus, you've got this nice picture that's backing up the calculus. That is, you have the picture that gives you intuition about what the mathematics tells you, and the visual kind of says, oh yeah, we've got this black hole here, we've got this infinite gravity going on. And then now, just like we had before, we had that little blip up here with the slant asymptote, there's nothing we can do here. That is, we have to approach x equal 1/2 in a negatively infinite way as we approach from the right. So we're doing something like this. And then we have to approach y equal negative 1/4 and all below the x-axis. So we can easily draw this. Like that. So the nice part about this is that, again, this looks 1-to-1, but we didn't think about trying to draw it 1-to-1. It's just that what we have is a situation where in both cases, the graph approaches the horizontal and the vertical asymptotes. Again, remember, you never cross a vertical asymptote. It is possible to cross a horizontal asymptote. So what we have to do when we look at these types of problems is simply, again, get all of the basics that we can outside of the calculus. So again, another nice calculus problem would say, okay, prove that the function increases throughout its domain. Prove that this function increases throughout its domain, just like we've drawn it here. It looks like it does. It does look like it's increasing, but that's not a proof. So that would be a calculus problem. And then, of course, there could be a second derivative problem where you discuss the concavity. And then you might ask a question, prove that the function has no relative extrema, that it has no peaks and valleys. So when you look at this, you can again say, okay, based on what we've done here, we have a domain of R, which will be all real numbers except 1/2. And then the range, it appears, in this case, and we could prove this, that we never hit the output of what? The horizontal asymptote, negative 1/4. Even though in other rational functions, we could actually hit the horizontal asymptote. So one thing that's interesting about this function is because we can prove that it's one-to-one, we don't get this crossing bit, because if we did, that would violate the one-to-one. So there's got to be some give and take here. The mathematics we do here has to be supported by the mathematics we do in another place. And that's really why we have to make sure that as we take mathematics to a new course, we have good mathematics and not a bunch of errors that would get in the way. Now, another example that will be of use to us let's look at a situation where we have a couple of vertical asymptotes. Now, you don't have to, just go with what I'm doing. You can do additional problems in your book. You can look at some of the practice problems in the practice test section, and you can make up your own. There's nothing bad about that. Make up your own asymptotes, have it already factored form. So here we have R of X equals 3x squared. And then of course, next week we'll start our exponents and logs. So in more review of the college algebra. So when we look at this particular function, we have R of X equals 3x squared plus 6 divided by x squared minus 2x minus 3. And when we look at this, we're thinking, okay, well, we got the same degrees, but before we, do a little bit with that, let's go ahead and factor, because we have some obvious factoring. 3 times x squared plus 2. And then, of course, the AC here, we see that we can use a -3 and a 1 because that would sum to -2. And of course, the -3 times the 1 would give us the -3. So we could say x minus 3, x plus 1. So again, we can think of this as P of x over Q of x. And now, just looking at it from the standpoint of degrees, we see degree of P equals 2, degree of Q equals 2. So this implies horizontal asymptote. And we just do ratio of leading coefficients. So we can just look right here. So y equals 3 over 1 or 3. So again, you can look at the particular examples and see that the dominant terms control the size of the function when x becomes arbitrarily large or small. These other terms, they just are insignificant. And so what happens is that these x squares absorb, and the only thing that's left behind is that factor of 3 over 1. So it's like when the x is large, the only thing that really matters are these two terms. And that basically gives you 3. So the intuition that we get from thinking about these limits at infinity with the horizontal asymptotes is good because it is supported by the mathematics. So it's not always the case that the intuition will lead us correctly, especially when we think about function transformations in the horizontal sense. They're always counterintuitive. So when we look at this, we're like, okay, so we have a horizontal asymptote, y equal 3. Now, for the vertical asymptotes, just like we did before, we look for zeros in the denominator. But let's first notice that the numerator is never 0. It has imaginary zeros. We would say plus or minus square root 2 times I. We've done this when we did the complete factorization with the fundamental theorem of algebra. So this does have zeros, but they're not going to be real zeros. So we don't have to worry about them. So now we see that we have zeros here and zeros here, a 3 and a -1 that will never be zeros in the numerator. So this gives us x equals 3 x equals -1. So we've covered the asymptotes, and now just look at the intercepts. Well, we've already beaten that to death. There are no x-intercepts that are real, so we have none. So we're just saying imaginary zeros. That really interesting problem we did with the polynomial that had the imaginary coefficients, you treat it just like a quadratic equation. There's no difference. That sometimes you may come up with some arithmetic that'll look kind of strange, but again, we normally just think of the quadratic formula when I've actually completed the square. We just thought about the real coefficients, but they don't have to be real. So we kind of see what can happen as you get more different kinds of polynomials. And now for the y-intercept, we look here and we just replace x with 0. So r of 0. So all of these terms go away and we're left with 6 divided by -3, which is -2. So what's interesting about this particular problem that we did not see in the last problem is that what's going on with the horizontal asymptote. And often we, like I say, you can't just say, okay, for this rational function, this is what happens. So this must be a lemma. No, we're going to find in this case that crossing the horizontal asymptote is indeed possible. And again, it's going to become another calculus problem. So with that in mind, first, let's look at the actual sign test. So we don't have much to contend with except for the BVs that we have in the denominator. So BVs are just 3 and -1. And so if you like, we can just think about this here, like say maybe a -10, a 0, and a 5. But notice the numerator is always positive. This is always positive. And so here we'll get a negative and a negative. So we have a negative times a negative, which is plus. So we're above the axis. But again, these are just first degree zeros. So we're above, and then we're below, and then we're above. So again, we don't cross, because that's why I don't continue the line. We don't cross. But again, the multiplicities dictate the fact that the sign must change on either side of the vertical asymptote. That theory is still in play. So like I said before, if you're comfortable with this, fine. Otherwise, you can just check the zeros. If we have two negatives, like we put in a negative, 0 here, we get negative. We put in 0 here, we get positive. So this is overall negative. And then for the 5 here, we get plus and plus. So that is still the same. I just want to make you aware that it's also possible to look at the multiplicities here. But that's neither here nor there. If you want to use that, fine. Otherwise, you can do as I've done here in the alternate approach. So now all we want to do, and I'm going to do a little side calculation later, but I want to go ahead and draw the axes. Now, of course, when you're doing the WebAssign, in a lot of cases, you'll just pick from a graph, but you go ahead and do the sketch yourself. Now, notice we have, in this case, 3 and -1, and then we have a -2. So we can spread this out a little bit. So let's just say we have 1, 2, 3, and then we've got a -1. And then for the y-intercept, we've got a -2. So we can spread this out a little bit. So we'll say 1, 2, 3 to get the horizontal asymptote, and then 1 and a 2. So -2, 3, and then we have a -1, and we have the 3 here. And then what we can do is go ahead and sketch in the vertical asymptotes, or just sketch them. And then the 3. And then we have y equal 3. So y equals 3. Now, what's interesting about this particular setup is that we've got this y-intercept right here. So let's go ahead and look at this part. Between -1 and 3 here, we're below the x-axis. And so we've got to -infinity here, pick up this point, and then proceed back down to -infinity. So we're not really sure where the maximum is going to be, so we're just kind of guesstimate. Something like this. So we don't really, like I say, we don't really know where the relative maximum is here. We pretty much believe there is one because the function's nice and smooth. So it would have to transition through at least one horizontal asymptote to go from increasing to decreasing. So the calculus would be the only way to give us that. And then on this side here, again, as we approach 3 from the right, we've got the left already, we're approaching positive infinity, and then we have to approach here, okay? So we're thinking that, okay, are we gonna actually cross here or cross there? So let's do, before we do this, let's do a slight computation here, because notice on this side, we're above. So do we just kind of do like this and stay above this line? Do we cross it? Are we below it and then cross it? We're not sure because again, this is quadratic in P and Q. And so we can't just say, oh, well, it's not going to cross. We would have to check. And so here's a check. So we'll have 3x squared plus 6. And again, if you didn't notice this, it wouldn't matter. If you're picking a graph from the WebAssign, the others wouldn't make any sense. And you'd say, well, this is the closest one. So, oh, look what's going on there. That's what you would notice when you would pick it. And so you're saying, is it possible that the output of this function could actually coincide with the horizontal asymptote? And I think you might be surprised that it does. So we have a 1 here. So let's cross multiply. 3x squared minus 2x minus 3 equals 3x squared plus a 6. And now 3x squared, well, that's good because the square terms are going to absorb, minus 6x minus 9 equals 3x squared plus 6. So the square terms absorb. And then we get a negative 6x. If we add 9 to both sides, that'll give us a 9 plus a 6. Well, boy, easy arithmetic compared to the word problems that we did with all that symbolic computation. And so x equals, so that'll be what, 5 times 3 divided by negative 2 times 3. The 3's absorbed. And so that gives us a negative 5 halves. So indeed it does. So we get the point negative 5/2, which is negative 2.5, 3. So when we go here, we need to plot this. So that'll be a 1, a 2, a 3. So about right here. Run this up to right there. So we have the point negative 5/2, 3. So indeed, the graph crosses the horizontal asymptote. So it's got the hug here. This is where we have to kind of guesstimate hug, maybe droop down a little bit and come through. And then off to positive infinity. So when you got something going on like this, the calculus will actually tell you where this dip is, where the minimum is, because we're thinking, well, it's going to dip a little and then move back up. We're not really sure, but in order to cross, it must have this configuration. It can't be up here and then cross, because the function has to become at -1 positively infinite from the left. So this is where this little sign test gives us all the information we need, at least for a cheat graph. So as we approach -1 from the left, the approach must be in the positive infinity sense. So we would have to start here and then cross. We could not do the opposite. So the arithmetic that we see in the sign test gives us loads of information. And you cannot discount this, because if you do, you're just making it up. If you don't know why you're sketching a function at least above or below the x-axis, then stop and do the sign test. Don't guess. You can often use points and say, well, I've got to pick up this point, so I can't be up there. That would be a good choice. But over here, we got to do a little more analysis. And so now for this side, we know that we have to approach positive infinity here. And then we've got to approach the line y = 3. And we can't cross because there was only one place that we crossed, and that was right there at -5/2. So here we'll get this. Like that. So our reasonable graph has a little kink in it right here. But again, if you were doing this analysis and you really weren't sure here, you would say, oh, there's my graph, and oh, look what's going on. We're actually crossing the horizontal asymptote. So when you're dealing with a lot of situations like this, that is where you actually have a horizontal asymptote that is the ratio of two leading coefficients, where these are both quadratic. This is a common occurrence. I remember when I first started teaching, I would teach some business calculus, and they never liked these problems. They say, oh, Professor Ron, don't put one like this on the test. I said, well, you know, it doesn't matter. I said, they didn't even want to do the calculus part, and it was a business calculus class, but that's neither here nor there. It's just that with this type of condition, this is a common occurrence, a very common occurrence. And you could actually do some more investigating of this if you like. Now, what I want to do, so that kind of covers the rational functions, maybe more than you wanted to hear. What I want to do now is look at another example with the inequalities. And I just worked this out, and I just want to just kind of uncover it and then do an example that I have yet to allude to, just to give you some additional insight. Now, what I did say is that I would come back to the inequalities, just to kind of give you a reminder of where we've been. So what I've done here, ladies and gentlemen, is I've said solve the inequality. Now, this doesn't have the same form as the last one did, But this is something we already know how to do, but maybe we want to infuse a few new ideas in the process. Now, when we look at this, the first thing I said when we reviewed this is that we need to compare everything to 0. So the very first thing you need to do is to achieve the 0 on the right-hand side. So if we have x over 2 is greater than or equal to 6 divided by x plus 1 plus 5, then that's really kind of a nightmare if we're trying to determine in some kind of organized way what values of x work other than just guess and check, which is not a bad way to do things if we just need a couple of values of x. But we're looking for all of them. So to do that, of course, we subtract both of these terms from the right-hand side and put everything on the left to achieve the 0. So we have x over 2 minus 6 divided by x plus 1 minus 5 over 1, which you've done in your polynomial or in your inequality section. Now, the next thing, again, we want to think about a BV technique. And so we think, okay, what's the least common denominator? Well, we're really good at this. We've got a 1 here, we've got an x plus 1 here, and a 2 here. So the least common denominator would just be 2, the factor of 2, times the factor of x plus 1. And so that there we have here. And then we make some adjustments. We want this to be equivalent. So we've got the 2 here, but not the x plus 1. So we multiply the x plus 1, the x times the x plus 1. Here we have the x plus 1, but not the 2. So we multiply the negative 6 by the 2. And then the negative 5, well, all it has is the 1. So it gets the 2, which creates the negative 10. And then, of course, the x plus 1. So now, what we want to do is combine terms. So again, x times x plus 1 gives us x squared plus x. And then we have a negative 12. And then, of course, a negative 10x minus a 10. Now, I'll go ahead and pull all this away. That'll take me to this example over here. And now, when we combine terms, we got x squared, and then we have a negative 10x, and we have an x, which gives us a negative 9x. And then, of course, the negative 12 minus the 10 gives us a negative 22. Now, again, this is a very simple situation. With the AC here, you notice we have the 1 times the negative 22. And that just, again, ignore the 1 and just write the negative 22 is negative 11 times 2. And of course, if this is the Z and this is the W, their sum is negative 9. So that's a good, simple one. We really do like the ones that have the leading coefficient of 1. They make our lives so easy. And so we get x minus 11 times x plus 2. And then we're ready for the BV technique, so to speak. When you look at this, we see that we, and of course you could look at this as just a rational expression and see that we would have a slant asymptote, but we've already done that. So we get a negative 1, we get an 11, and we get a negative 2. And so what I did here was kind of take advantage of the fact that, again, we have the multiplicity of 1 in all these zeros. So the first thing we could do is plot these. We'll have the negative 2 here, and then the negative 1, and then the 11. And so to kind of get the ball rolling, I went ahead and checked here the negative 10. So the negative 10 in here will give us a negative factor, the negative 10 here, a negative factor, and the negative 10 here, likewise, 3 negatives, negative. So the idea is that now we have negative below the x-axis, so to speak, and then at all of these zeros, we have odd multiplicity. So the sign would have to change. Of course, here we don't cross, but we cross at negative 2, and we cross at 11, and then we just change sign when we think about the vertical asymptote. So again, negative, positive, negative, positive. So you can get the ball rolling, and then focus on the multiplicities to move the problem forward. And it is somewhat of a time saver, but it's only a time saver when we have these nice factors and we know what's going on. The interesting thing is that if there's any uncertainty about using this technique, you just check the factors as I have taught you. But I want to make you aware that in these cases we can use multiplicity. Now we go back to the original part of the problem and see what is this equivalent to that helps us out. We see now that the entire problem has come down to this. We need either 0 or positive. So when we look at this, we see at 11, we get 0, and -2, we get 0. So we get checks in both of these cases. And then of course at -1, it's undefined, so that gives us an X. But now of course we have positive here and positive here. So if we follow all of the checks, we see that we start with a bracket. And in this particular case, let me put my negative here. We have -2. And then we increase to -1, but with a parenthesis. We don't include the -1, it's undefined there. That would not make any sense. And then we exclude this area. Then we tend to the 11, which again makes this 0. We include with the bracket. And then of course we extend to positive infinity, close with the parenthesis. And so I remember a student saying one time, WebAssign likes to close things for me and you know, close parentheses and all. And I said, that's fine. I said, but make sure if they're closed or whatever, that you have the correct bracket or closing structure. If you need a bracket, put in the bracket. If the parenthesis is fine, then leave it alone. A lot of the built-in features of the computer algebra system can be very time-saving. But then you have to go back and check and say, well, am I using the right variable? Well, I don't need variables here, but let me check my work and make sure that I'm actually typing exactly what I've written on the page. And does this correspond with this? You know, so again, it's always lots of checking that has to be done. So again, aside from the rational zeros theorem, most of these problems you will find will remind you of problems we've already done. But I want you not to forget about this. We will actually do equations when we study trigonometry. There will be lots of arithmetic type operations that we do. So we won't lose any of that. But this kind of technique that you will need in calculus can sometimes get a little bit rusty. And then when we move to conic sections and sequences and induction and binomial theorem, some of this tends to get rusty. So I want you to make sure that you have a good command of this. So when you see it again in calculus, it's just not, you know, so far gone that you have to start over. Now, what I wanted to do, and we'll do a little bit more with this, is to look at situations that arise with vertical asymptotes and the existence of no vertical asymptote. So here's an example. I want to give you, I'm just going to make up a function. Let's call it t of x. And let's see here. I'll say 2 times x minus 2, x plus 3. And here I'll do x minus 2, x plus 3. So if you saw on the previous page where I had the inequality, I'd made up one, and you're thinking, why are you doing this one? That one looked easier than this one. Well, that's my choice. Now, my question to you, well, this is clearly a rational function, okay? It's clearly by definition a rational function. And my question to you would be, what are the vertical asymptotes? And so, does anyone know what the vertical asymptotes are? Don't everybody be bashful.
Is it 2 and -3?
What now?
Is it 2 and -3?
But what, Noah, what's a vertical asymptote?
I just know that it's equal to 0.
Okay, so when you state a vertical asymptote, tell me how do you write it?
I usually set the denominator equal to 0.
Right, so what would the equation look like? You'd say x equals what?
I would put x minus 2 equals 0, and then x plus 3 equals 0.
And so you're saying the vertical asymptotes would be x equal 2 and x equal -3.
Yes.
Okay, well, okay, so you get a half a point for that, all right? Okay, now, does anyone agree with Noah? I like the fact that that's how you came up with the statement of the vertical asymptote. That's why I gave you a half a point, but I didn't give you 10 points, did I? Why didn't I give you 10 points?
Because the numerator also has the same zero.
Yeah. So Noah, you get a half a point for giving me a good technique. But notice and Noah, I'm gonna give you 10 points anyway, and Brian, I'm gonna give you 20 points. So here we go. So that's a real democracy, right? My goodness, it's a dictatorship because Professor Ron is in charge. Now look at this, everybody. Brian made out a point here. Notice Q of 2 equals 0. And this is what Noah helped me get. Q of -3 equals 0. What is P of 2? What is P of 2? What happens if I put 2 in the numerator?
0.
Oh, okay. What's P of -3?
0 as well.
Oh, okay. So does the x equal 2 and x equal -3 define vertical asymptotes by definition?
No.
No, very good. There you go. So this implies
I wouldn't have
no.
any.
Right. And you know what? This might be a 10-point question on the next test. No vertical asymptotes. What do we have instead? We have holes. So note, T of x is a function with 2 holes. Where are the holes? Well, we're going to have 2, 2, and -3, 2. Because look, what does this equal? This function equals 2 when x does not equal 2, x does not equal -3. And it is undefined when x equals 2, x equals 3. So let's draw it. Not that we need to. So true or false, T of x becomes infinite. False, right? How big can it be? 2. How small can it be? 2. So there's 2, and we'll do 1, 2. So I'm going to put the circle here. I'm going to put the circle here. And here's the graph of the function. It's a horizontal line with 2 holes in it. That's T of x. Don't forget that. So this is what I mean, and Noah and Brian, thank you for this, because that means you're thinking. I don't even care if you give me an answer that's not completely correct. As long as you're thinking, you can extend what you know. So remember, when you have a vertical asymptote, it must be the case that the 0 only exists in the denominator. If it exists in the numerator, then you develop what we call a hole in the function. The function doesn't even become infinite in this case. You get a function that is 2 for all values of the domain. So I want you to keep this in mind because this is a very popular calculus problem. Functions with holes in them make great limit problems. And when you get to Calculus 1, that will be one of the first topics that you cover, functions with holes in them. And they occur in calculus all over the place, and you begin to think differently about mathematics when you start to learn calculus because you fill in all the details. Okay, this was good. Thank you, Brian and Noah, for your input. It does make a difference when we have input, and I know that you're thinking. All of you think very well, and I appreciate that. So what I want you to do is go ahead and complete the sections on the rational expressions, on the complete factorization, and go ahead and review the inequalities that we've done. And also think about what we're going into the future. We're going to be doing the basics on the exponentials and logarithmic functions. So if you get finished with this and you want to work into that, that'll be fine. I've already posted those sections. But I appreciate your time today, and I appreciate the fact that you're working very hard to get this into your brain. Just remember the goal is calculus, and the goal is understanding of calculus, and these are the raw materials. So thank goodness it's not raining anymore. Hallelujah. Things will dry out. And I know I shouldn't be saying this because then we're probably going to have a drought. But Professor Ron is happy that it's not raining. You all have a great day.
You too.
Yeah.
Thank you.
Thank you.
Bye.
Thank you too. Bye.
Bye. You know, this is such a positive class. I really appreciate that. I like students who love to learn, so thank you for that.
Thank you for teaching.
Oh, absolutely, anytime.